Okay. So I'll repeat a few things here. The bottom element of this post set of Boolean subalgebras is 0, 1. It has a top if and only if the whole thing is Boolean. And so in general, it's a post set, not a lattice. Okay? This post set is atomistic, and the atoms of this post set are 4-element Boolean subalgebras. So a 4-element Boolean subalgebra is given by an element of your orthomodular post set A that isn't 0 or 1. Okay? So you can figure out how many elements A has by taking the atoms and doubling them. Okay? And then you have to do something with 0 and 1, right? So the elements of this post set of height 2 are 8-element Boolean subalgebras. So a little bit trickier is that 2 atoms will have a height 2 join. So what does that mean? Having a height 2 join means that these 2 guys are both sitting inside of some 8-element Boolean subalgebra. Well, how can that be? It has to be, so if you think of an 8-element Boolean algebra, it's not very big. And we have A and A prime aren't 0 or 1. B and B prime aren't 0 and 1. You're going to have a comparability among one of these guys and one of these guys. And that's if and only if. Okay? So the point I'm trying to get across here is that you naively think that this post set tells you a lot about A. I can sort of figure out how many elements A has by just doubling the atoms. And I can sort of figure out something about the ordering of this guy by looking at when atoms have a height 2 join. So you might hope that from this post set, I can figure out A. And for the most part, it turns out that yes, you can do that. So one last little bit here is that turns out that this guy is an atomistic meet semilattice, and each principal down set is a partition lattice. So you can figure out a lot more about this post set. But that's not the direction I want to go in so much. All right, now let's change this just a little bit. By B sub A star, I'm going to not consider all Boolean subalgebras of A, but just those with at most 8 elements. So just the very bottom couple levels of this post set of Boolean subalgebras. We can draw this guy geometrically. We can draw it with points for atoms. So here's A. So A isn't very tall. Its whole thing is short, so you won't see it. But to give a big picture is sort of ugly. So the point I'm trying to get across here is the geometric way to draw it. This picture here is the same picture that I have from this slide. What's new is I'm going to draw this guy geometrically. So these points here, these atoms, are going to be drawn as points. The guys of height 2 are going to be drawn as lines. So these are 8-element Boolean algebras. So each 8-element Boolean algebra will have 3 4-element subalgebras. So each line will have 3 points on it. So I can get a sort of geometric type of picture with points and lines to draw this guy. And in this simple case, what I'm getting is, this is actually the Gricci diagram of A. So let's go just one little bit farther. Instead of confining myself to 8-element Boolean algebras, I'm going to show what the B sub A star is for a 4, 8, and 16-element Boolean algebra. So a 4-element Boolean algebra has exactly a 4-element Boolean algebra as a subalgebra and just the 2-element guy. So it's a single point. An 8-element Boolean algebra is a line with 3 4-element Boolean subalgebras. So it's a line with 3 points on it. Now a 16-element Boolean algebra it takes a little bit of doing, but it winds up looking like this. It's more or less the Fano plane missing a little bit, and that's not a coincidence, but we're going to call this a point, call this a line, and call this a plane. Okay, so here's what we'd like to do. The naive idea that we had of recovering our orthomodular poset from this short poset or from this geometric figure that we get is, the idea is to have a direction. So let's try to remember a couple of things here. In this picture, a point is a 4-element Boolean subalgebra, 0, A prime, and 1. That's 2 elements of our original orthomodular poset, A and its orthocomplement. And the idea is I want to somehow pick out which I want to associate with this point 2 elements. And what I'm going to do is I'm going to have something called a direction. The direction will have, each point will have 2 directions, up and down, one for A and one for A prime. So what a direction for a point is it's an assignment to each line that contains this point of a direction, either up or down, subject to the following little condition. So, what does this little condition say? If we require that our direction takes different values of up and down on 2 lines that contain P, if and only if these 2 lines are coplanar, which means they lie in a plane. Remember, a plane is this kind of thing. And they're the only lines containing P in the plane that they determine. I'll try to explain where this comes from in a minute, but that's what a direction for a point is. Now let's see where this comes from a little bit. Okay, a 4-element Boolean algebra, or a point, can sit inside an 8-element one, a line, in 2 ways. It can sit in there with A being an atom, or with A being a coatom. If A is sitting inside as an atom, we're going to assign it the direction down, and if A is a coatom, we'll assign it the direction up. Now the idea is that if A is a coatom of one line, so here it's an up, and it's an atom of another line, so it's got the direction down here, then I have a 4-element, so this is all taking place in our original orthomodular poset A. I have a 4-element chain. I have, what is it, B less underneath A, underneath C. So this 4-element chain generates a 16-element Boolean subalgebra, in other words, a plane. And then it sits exactly as this. Okay? So it's a fairly straightforward condition. Now, here's how you go about reconstructing an orthomodular poset from this short guy. So for G, the geometric diagram of this guy, okay, the short, let the directions of G be the set of all directions of points of G plus 2 new elements, 0 and 1. Now, I put operations prime and orthogonal join on directions of G as follows. How do I make the orthocomplement of a direction? I just enter, whenever my previous direction D was up, I switch it so that D prime is down, and vice versa. And to define the orthogonal join, if D is a direction for P and D is a direction for Q, then D plus E is defined if and only if these 2 points lie on a line and satisfy this somewhat cryptic condition that I won't go through and explain in detail here. But the point is that in a fairly straightforward way, I can reconstruct my orthomodular poset from this geometric configuration. And the theorem is if A is a non-trivial orthomodular poset, then A is isomorphic to the directions of G. All right, so you might then ask, can you characterize the posets or the geometric configurations that you that arise in this way? And you can, and it's fairly simple, is that you require that every line has exactly 3 points. So I have a bunch of points and a bunch of lines, like in projective geometry, that 2 distinct points lie on at most of one line, that each triangle, so a triangle is 3 lines that pairwise intersect, each triangle lies in a plane, and crucially that every point has a direction. And so if you have that, that is one of these guys for some orthomodular poset, A. You can also characterize the bigger guys, but it's a little bit more cumbersome, and I won't take the time to do that. So just to recap, you can determine an orthomodular poset from this geometric configuration that you get from its small Boolean subalgebras, and that you can characterize which these are in terms of simple geometric conditions. Well, maybe this one isn't quite so simple. Now, applications to operator algebras. So if you have a C-star algebra A, so basically if you don't know, think of this as a matrix algebra, then you can define a new product. So the multiplication of a C-star algebra is not commutative. You symmetrize it, and this is called the Jordan product. Now, a C-star algebra is not determined by its Jordan product, because a C-star algebra and its opposite will have the same Jordan product. But a C-star algebra and its opposite will have the same poset of abelian subalgebras. So here, I'm going to pass to the poset of abelian subalgebras of a C-star algebra. It's the correspondent of the Boolean subalgebras of an orthomodular lattice. And here we mean unital abelian subalgebras. And using Dye's theorem, using Dye's theorem, we obtain the following, and this was Andres Doring and myself, that of a Neumann algebra without type I2 summoned, and here we'll go back to Thomas has talked about how really short things are bad. so here, the hopeless. So an I2 summoned is basically coming from a 2-dimensional Hilbert space kind of thing. But if you have a von Neumann algebra without a type I2 summoned, it's determined up to Jordan isomorphism by its poset of abelian subalgebras. And Jan Helmholtz has a corresponding result for C-star algebras that came out of here. So there's an application to operator algebras. Now, I don't have time to talk very in detail about what the topic of topless quantum mechanics, but and I'm an agnostic in terms of this subject, meaning I'm not an advocate of it. I'm not a detractor from it. It's not something I've ever made the focus of my work, but what we were saying about Boolean subalgebras is related to it, so I'd like to talk about that. So very quickly, you can, if you have a poset, you can get a topless in many ways, but if you have a poset, you can look at the topless of presheaves on a poset. And this is the central ingredient of Topos quantum mechanics. And the idea is that abelian subalgebras of a von Neumann algebra, or in other words, the Boolean subalgebras of its projection lattice, correspond to classical snapshots of a quantum system. And somehow it's these classical, what a topos does is it glues together little pictures of things. And so by gluing together these classical snapshots of a quantum system, the topos gives you the complete view of quantum mechanics. As an example, the state space of a quantum system is what's called the spectral presheaf that assigns the stone space, sigma b, to each Boolean subalgebra of the projection lattice of your von Neumann algebra N. And probably certainly a very nice result from Topos quantum mechanics is the Koch-Specker theorem is equivalent to this presheaf not having a global section. So this is a complicated subject to develop. There's thick volumes given to developing this, and I'm not going to go too deeply into it, but I'd like to make a couple little points about this. It seems that probably, as far as I know, all of this approach can be done instead of taking this poset, which is all the Boolean subalgebras of the projection lattice of your von Neumann algebra. So this is a big, complicated poset. It's infinitely tall if this guy is infinite dimensional. Instead of using this as the basis of your topos, which leads to very complicated arguments in developing all these presheafs that you need, you can instead use this very short poset, and you more or less get rid of all the infinite arguments in developing Topos quantum mechanics. So it really, if it's your aim to do Topos quantum theory, this will cut your work significantly. So there's one point. Another thing is that you get a geometric view of the base space that you're using. So this poset is, in my view, it's nice to have this geometric perspective of this poset. And while I haven't spoken about it, you can define morphisms between these geometric objects, much like you do in projective geometry. And take a little catchy phrase that is, instead of using 10 megapixel classical snapshots, which is fitting because Andreas Doring is a photographer, you can get by with just little glimpses, so little tiny Boolean subalgebras. Okay, so let's see. So I was going to talk about several things. So the Boolean poset of subalgebras, applications to operator algebras, applications to Topos quantum mechanics. And so this last little bit is I'd like to talk about some logical connections. So a monadic ortholattice is an ortholattice L with a map exists from L to itself that satisfies these properties. So essentially what it says is it's a closure operation where the orthocomplement of a closed element is closed. And monadic Boolean algebras, well, they're never called that. They're just called monadic when the underlying lattice is a Boolean algebra. They're algebraic models of the one variable fragment of first order logic, so hence the name monadic for one variable. And they're introduced by Helmholtz back in the 60s. So if L is I'm going to switch here to, I'm going to add the assumption for our discussion here that L is a complete ortholattice, and that C is a complete subalgebra of L. By complete subalgebra, I mean C is an ortholattice. It's a subortholattice of L. It's not only is it complete, but that all joins and meets in C are as they are in L. When you have such a thing here, when you have a complete subalgebra, for any x in L, I can define this. I can find a smallest guy in C that's above him. Namely, I take the mean of all the things in C that lie above x, and that gives me this map exists that's called a quantifier. I don't know if I said that, but this kind of a map is called a quantifier. I'll use that again. And similarly, there's the largest guy in C that's underneath x, and that's written for all x. Now, every quantifier on a complete ortholattice arises in this way. So instead of talking about quantifiers, I can talk about complete subalgebras, as long as I'm in the setting of L being a complete ortholattice. So here are some examples of monadic orthomodular lattices. So I'm going to assume that L is I'm going to assume, well, here, let me just go through them. If L is a complete orthomodular lattice, every block, so maximal Boolean subalgebra, gives you a complete subalgebra, and so that gives you a quantifier, so a monadic orthomodular lattice. If I have a von Neumann algebra, N acting on a Hilbert space H, then the projection lattice of N is a complete subalgebra, the projection lattice of H. So this is an example of a monadic orthomodular lattice as well. And if I have a subfactor, so M and N are both von Neumann algebras, and they're both factors, and M is a sub von Neumann algebra of N, unital, then this again gives me a subfactor, or this again gives me a monadic ortholattice. Okay, so cylindric algebras were introduced by Henkin and Tarski to study the full first order logic, and they're very closely related to Helmholtz's monadic algebra. So a diagonal free cylindric algebra, cylindric ortholattice is an ortholattice with a family of quantifiers that commute. It's a cylindric ortholattice if it has constants called diagonals. So diagonal free doesn't have the diagonals. If it has constants, Dij, for every pair of quantifiers that satisfy these conditions, they're symmetric, and D11 is 1, and this condition. Now, if you are well versed in classical cylindric algebras, I've left a condition out here, and a useful condition, and it seems you can't get away with including it because it's the condition that with the others gives you a substitution. And if you think of the projection lattice of a Hilbert space, substitution is going to be an endomorphism, and you're going to have difficulties getting an endomorphism. So examples of cylindric ortholattices, there's something called Nick Weaver's quantum logic. If you take a tensor power of a Hilbert space, then there are these subalgebras. They're complete subalgebras of the projection lattices. So right, if I have a projection, I just take its tensor product with the identities, and that gives you a projection here. And so these complete subalgebras give quantifiers, and they're commuting. So this gives you diagonal-free cylindric algebra, you can get diagonals using the symmetric tensor product. That's what Weaver does. And this gives you a cylindric algebra, but it doesn't work with substitution very well. You do have difficulties, and there are difficulties with Weaver's quantum logic for exactly this reason. And so if you're familiar, there's an axiomatization of what's called the cylindric set algebra, and there's a similar axiomatization of this cylindric or orthomodular lattice. There's another example of a diagonal-free cylindric orthomodular lattices. I'll restrict to type 2-1 factors here. So if I have two subfactors, type 2-1 subfactors of a type 2-1 factor M, then these are equivalent. Each one will give you a quantifier. These quantifiers commute if and only if these form what's called a commuting square of subfactors, which is a interesting topic in subfactor theory. And commuting squares of subfactors, roughly they correspond to independent sigma algebras in the classical setting. And orthogonal subfactors are a particular example of a commuting square of subfactors. So there's a nice, simple, logical way to view an interesting operator theoretic notion. I'm out of time, so let me quickly mention that the way Thomas did things with orthogonality spaces, that I'll be very brief about this. If you have a cylindric, if you have a monadic ortholattice, it has a dual space that's produced, that's an orthoframe, and you can do this in one of two ways, the way Maclaurin did it or the way Goldblatt did it through the filters. And if you're familiar with classic monadic algebras, you can add an additional relation, an equivalence relation onto your orthoframe, and you get, by doing this, you get the canonical completion of the associated monadic ortholattice. So, okay, thanks very much.
Thank you. Just one short question and shorter answer, please. Yeah?
Thanks. Thanks, John. So just about this failure of or difficulty with the diagonals, I wonder if this does this have a natural kind of physical interpretation? For example, you could imagine it was related. I mean, problems with substitution might relate to no cloning or something like that. Yeah. But you haven't specifically related it to something like no cloning.
Well, Andre Cornell has a limited version of, it's limited in a good way, if you understand what I mean. It's introduces duals so that you have this kind of, you can talk about it in a setting. So I'll let him explain it, but it's he has a limited version of this where you can talk about the problem. So it gives you, in a way, it gives more than what this does because he's got troubles with quality. He says you have troubles with quality in general, but not. And he can talk quite a bit about the physical motivation.
Thanks.
Okay, so let's thank the speaker again and move